Welcome back. So we were talking about leveling effect of water whenever we dissolve an acid or base in it. Okay. Now, in order to get strong acid, you need to accommodate or stabilize technically the conjugate base. Remember, your base is going to have a negative charge, so it will not be happy. Or if you generate, carbocation, that carbocation also will not be happy. We have to do something about it. And so, for example, we have, ethanol. If we take H from it, and that's going to give us ethoxide. That one will have -1 charge, or a tertiary butanol, and that one, again, it will give you O with a negative charge. Those two, they need to be stabilized. Okay, when I say stabilized, we need to distribute the negative charge or take some of the negative charge from oxygen and make it happy. But right now it has a negative charge. And whenever they get in water, and say this is our molecule, and there's oxygen there, and oxygen, it has 3 lone pairs on it. Water is going to surround it, and water is going to try to build kind of such a shape or cage around it. So let's say we have a cage around the ethoxide, and on ring you will have hydrogen atoms there. Okay. And I'm going to tell you why we're going to have hydrogen atoms here. Okay. And each one, each hydrogen is attached to oxygen, because attached to oxygen, hydrogen is going to have a positive charge. So you put a positive charge on hydrogen atoms. And of course, you're going to repeat this one for rest. And say we have oxygen somewhere there. Okay. All these hydrogen atoms come with positive charge. Okay. And oxygen has a negative charge. Remember that one. Okay. So the negative charge on oxygen will be distributed to those technically hydrogen atoms. Okay, or those hydrogen atoms try to take some of the negative charge. How? They're going to have some interaction with oxygen. Remember, we used to call this one hydrogen bonding. So we're going to have, some interaction. Now, these two, they're going to have a hard time to reach oxygen. Why? Because this methyl group is going to block them. Okay, so this hydrogen, it cannot really make it to oxygen, because the methyl, remember, any methyl, it has 2 hydrogen or maybe 3 hydrogen atoms attached to it. So oxygen, it will be blocked. The more bulky group you have, the harder it will be to technically diffuse and see the oxygen. So what I'm going to do, next step, instead of putting hydrogen here, I'm going to put, let's say, I'm going to put carbon atoms and see what will happen. I'm going to try to make this one bulky. Okay, so we're going to copy paste this one. And next time, I will put a bunch of methyl groups. Okay, so this is going to be one. That's the first one that I added. And this one is the third one. Okay, so and what happened? In this case, that interaction, I'm going to lose it. This interaction is gone. Okay, that interaction, I'm not going to have it anymore. Okay, and to some extent, maybe that one also is going to be hard. Okay, it's going to be hard. Why? Because the methyl has some hydrogen atoms there, and those hydrogen atoms are going to block, this hydrogen to see oxygen, or that hydrogen to see oxygen. So as you see, now I have less, I have less hydrogen atoms that can reach oxygen. So we say the solvation, this is the term that we use, solvation. What does it mean? It means solvent is surrounding the ion. Solvent is surrounding the ion, and solvent trying to technically distribute the negative or the positive charge. Okay, and distributed over the solvent molecule. Solvation will be harder. It will be hard to technically hug and pull the negative charge or positive charge of from the ion. And because the solvation goes down, okay, the ion, and which ion? This is your ion. Ion will be less stable. Okay, because the solvation went down, we got less stable ion. And if it's less stable, you get less acidic. Okay, so I'm going to write it in another page because I need more space. So this is the molecule that we started with, and it turned to such a molecule. We have negative charge. Of course, we have hydrogen, and hydrogen is taken. So hydrogen is taken by, let's say, a base or whatever. Okay. We said if solvation, okay, or surrounding the molecule, the ion, okay, the ion, surrounding the ion to be, and like happen to be less effective. So if the solvation goes down, then our conjugate base will be less stable. Okay. So now you have an acid that is going to release H or give up an H, but it will generate a less stable conjugate base. Because we got less stable conjugate base, we say our acid will be less acidic. Or, okay, how about this? We say weaker acid. Weaker acid. Okay, so less stabilization for the conjugate base is equal to weaker acid. Okay, weaker acid. And I don't like, to maybe confuse, and I don't like to confuse you here, but later we will see that whenever the conjugate base is not that stable, it will be more reactive. And more reactive, that means it's going to be looking for H. So it's going to be looking for H plus, and it will turn back to this direction because it's less less stable. So it's too reactive. And if it's too reactive, it will try to get H from somewhere and get back to the starting point. And this is the, technically the salvation effect. So higher salvation, okay, the more stabilization we get, the stronger acid will be. Okay, let's move on. And what's the role of the counter ion? The counter ion, okay, counter ion is there to balance the charges. So for example, in this case, what's the role of sodium? If we track sodium, it has a +1 charge. So if sodium is a +1 charge, I'm going to write it the blue. This one is a +1. That means our ion is -1. Okay, the sodium here is a +1. So what's going to be the charge for? What's the charge for the OH? We know OH has a negative charge, and the negative charge of OH will be canceled by charge of sodium. Okay, so the role for counter ion is to balance the charge. We cannot have any compound with a positive or negative. Anything in nature must be neutral. So in this case, I'm going to say around this, we have sodium somewhere to cancel the negative charge. Around OH, we're going to have a sodium to cancel negative charge of OH. So sodium is not there, okay? Sodium is not inside the equation. Doesn't mean does not exist. It's just simply because it's not running any chemical reaction, okay? It's not handling any chemical reaction, and simply we erase it just to make the formula easy, and so then the student can, follow the instructor or the teacher, better. Okay, and last one is going to be the Lewis acid versus Lewis base. Okay, the Lewis acid and Lewis the Bronsted Lewis acid and base was this were this. We said acid is a compound that donating H, and a base is a compound that's going to accept H plus. Okay, that was the definition of Bronsted acid and the Bronsted base. Now, when we are talking about Lewis acid, Lewis bases, we are not going to be dealing with H. We don't care about H. The thing that we care about it will be lone pair. Are you accepting or donating lone pair? If you are accepting, okay, if you're accepting lone pair, okay, if you're accepting a lone pair, you will be acid. If you're donating a lone pair, you will be a base. Okay, I want you to be careful about the donating or accepting. Don't get confused with the Bronsted. Bronsted was saying the acid is the one that's donating H plus. Okay, donating H plus. And for Lewis acid, we say acid is a compound that's going to accept lone pair. Okay. Now, based on Bronsted definition, I'm going to call this one, okay, acid. Why? Because is giving, okay, giving, H plus to water. And this is going to be the base. Okay, that's going to be the base. Now, what should I call this? This one, it will be conjugate acid. Conjugate base. And hydrogen ion, it will be the conjugate acid. Okay. Now, if we are talking about Lewis acid, Lewis bases, H does not have electron. H is accepting electron. So I'm going to call it Lewis, okay? Lewis acid. And this is going to be the Lewis base. Okay. So the one that's donating lone pair, it will be the Lewis base, and the one that's accepting H plus, it will be, the one that's accepting lone pair, it will be the Lewis acid. Okay. Another example, water reacting with BF3. BF3 has an empty orbital. Remember, B is not octet. Okay, so B is not octet. Well, all fluorines are octet. Each fluorine has 3 lone pairs. So fluorines are octet. Now, how do you want to make, boron octet, share a lone pair from fluorine? But that's going to cost you energy. Or how about this? We have an empty, pi orbital, a p orbital, and that's a pz. Okay. And how about water? Water has 2 lone pairs. So water is going to give one of this lone pair and put those 2 electrons inside the empty orbital of a PF6. So water will be the Lewis base because it's donating lone pair, and the one with empty orbital, it will be the Lewis acid. Okay, this is not wrong to call H plus a Lewis acid. Why? Because, okay, if we reacted, for example, if we react this one with, say, OH, okay, we say the one that's accepting H plus, it will be the, acid, base, the one that is accepted, okay? So if we are talking about Bronsted, we say because H is going to OH, so OH, it will be the base, and H plus, it will be the acid. Now, if you're talking about Lewis acid versus Lewis base, H has an empty orbital, okay, and that's going to be 1s with no electron. How about OH? Oxygen has 3 lone pairs on it. Oxygen is going to put an electron inside the H plus orbital, and that's going to give you water, okay, with 2 lone pairs. So H plus, yes, is acid, based on definition of Bronsted, based on the Bronsted-Lowry definition. H plus also it will be Lewis acid. Why Lewis acid? Because it has an empty orbital. So this is going to be technically my last video for chapter 2. And next lecture, I will be talking about chapter 3. Thank you very much and have a good time.